Welcome to this video on the Fourier transform, where we will do an example of the Fourier transform of a square wave. Just as a reminder, here are the equations to calculate the Fourier transform. First, the equation where we have to do an integral for a naught. And then the equations to calculate the amplitudes of the cosines for the wave number k, the a sub k, where an integration is involved over the fundamental period uppercase T. And then the equation for the amplitude of the sine of wave number k, the b sub k, that involves an integral as well. So the example that we're going to do is calculate the Fourier transform of a square wave. In the square wave function over the fundamental period uppercase T is defined as g of t being equal to +1 if we are in the first part of the period from 0 to t over 2, and then equal to -1 if we're in the second part of the period. Okay, so task is to do this analytical Fourier transform. And what we'll have to do is plug in this definition of the function g into these integrals here and then evaluate all of these individual integrals. So let's begin with a sub naught. So a sub naught is this integral over here. So that would be 1 over the fundamental period t of the integral of g of t, but g of t is kind of piecewise defined. So what we're going to do is we are going to split this integral over here into a first part from 0 to t over 2, where g of t is just equal to +1, and then a second part from t over 2 to t, where g is equal to -1. Okay, so we do 1 over t, the first part, integral from 0 to t over 2 of g of t dt, plus the second part from t over 2 to t of g of t dt. And that's just, again, because there is a switch in the definition of g of t at t over 2. So then this would be the integral of 1 over t times the integral of 0 to t over 2 of g of t in this first part, right, is equal to +1. So 1 dt plus the integral from t over 2 to t of the definition of g of t in this interval is -1. So -1 dt. Okay, and those definitions, right, this +1 comes from this definition and the -1 comes from this definition in this subinterval that we're looking over here, and the +1 came from this interval from 0 to t over 2. Okay, so let's do this integral. It's 1 over t times integral of 1 dt is just t within the bounds of 0 to t over 2, plus or minus, right, I can pull out the sign, minus the integral of 1 dt is t from t over 2 to t. Okay, so let's plug this in. So it's 1 over t times, plug in the bounds, so t over 2 minus 0, minus the bounds of the other one is t minus t over 2. Okay, and you'll see that this will just be equal to, well, let's just do the operations, 1 over t times t over 2 minus t over 2 is t over 2 as well. So that's equal to just 0. So my a naught in this example is simply equal to 0. Okay, so we got this part here done. Next up is a sub k. So A sub k is equal to, so that's the amplitude for the cosine of a wave number k. And there's now infinitely many k values, right? They start at k equal to 1 and go all the way to infinity. And what we're trying to do is find a formula that is valid for any k value from 1 to infinity. So A sub k is, by the definition, 2 over t times the integral. I'm going to split the integral again from 0 to t over 2 because of the definition, right, that changes of g of t. If I'm between 0 and t over 2, then g of t is 1. So 1 times the cosine of k omega t dt plus the integral from t over 2 to t. And in this interval, g of t is equal to minus 1. So this is equal to minus 1. So minus 1 times the cosine of k omega t dt. Okay, so close the square bracket. So this is 2 over t times, well, first we have to integrate the cosine of k omega t. And if we integrate this, right, the integral of the cosine is the sine. But then we have these inner terms here, k times omega. So the integral is 1 over k times omega times the sine of k omega t between the bounds of 0 and t over 2. And then minus, okay, same thing, 1 over k omega times the sine of k omega t between the bounds of t over 2 to t. Okay, so let's plug these bounds in. So we have, first of all, 2 over t times square bracket and 1 over k omega times upper bound. It's the sine of k omega t over 2 minus the sine of k omega times the lower bound, which is 0. Then we have minus 1 over k omega times the sine of k omega t, upper bound is the period uppercase t, minus the sine of k omega times the lower bound, that's t over 2, t divided by 2. Okay, so then we can close all of these. All right, so now in this equation here, we have the omega, right, which is the fundamental angular frequency. But that omega, is defined as 2 pi divided by t. So let's substitute that definition in. So we have equal to 2 divided by t times, let's keep it here, 1 over k omega. Let's leave the omega there. Then the sine of k times omega, but omega is 2 pi divided by t, right? That's just this definition up here of the fundamental angular frequency. So k times 2 pi divided by t times t over 2 minus, well, here's the sine times k times omega times 0. That's the sine of 0. Well, that I know is 0. Right? The sine of 0 is always 0. And then we have minus 1 over k omega times the sine of k times omega, which is 2 pi divided by t, times t, minus the sine of k omega. Omega is 2 pi divided by t times t over 2. A whole bunch of parentheses that we have to close out. And now this is equal to 2 divided by t, 1 over k omega times the sine of, okay, so let's look at this guy here. So there's a 2 and a 2. So these two here, the 2's cancel, and the t divided by t, they cancel as well. So what I'm left with is k times pi minus 0, okay, minus 0, minus 1 over k omega times the sine of k times, over here the t cancels, and I'm left with 2 pi minus the sine of k times, and in these parentheses over here, the t cancels and the 2 cancel against each other. So we're left with the sine of k times pi. All right. Couple of brackets closed. Now, k is the wave number, right? So k, that is a whole positive number. So it's part of the natural numbers, excluding 0. So that means if k is a whole number positive, not 0, so it's 1, 2, 3, 4, 5, and so on. So we'll have to take here the sine of 1 times pi. Well, the sine of pi is 0. Then k can be 2. That would be the sine of 2 pi. Well, that's 0 as well. The sine of 3 pi is 0. The sine of 4 pi is 0. So actually, all of these here, all of these sine values are 0. So that's the same sine k pi here as well. That's 0. And then over here, we have k times 2 pi, where k can be 1. So that's the sine of 2 pi. That's 0. K can be 2. The sine of 4 pi is 0. The sine of 6 pi is 0. So all of these sine values here, they are all 0 as well. So everywhere in these parentheses here, the square parentheses, there's a 0. 0 minus 0 is 0 times 1 over k omega, that's 0. 0 minus 0 is 0 times 1 over k omega, that's 0 as well. So this entire parentheses, this entire term, is always 0 because k is a whole positive number, 1, 2, 3, 4, 5. So for any k value, be it 1, be it 2, all the way to infinity, whatever the k value is, this ak is always equal to 0. So ak is always 0, as was a naught we found up here. A naught is 0 as well. Okay, so we got this one here done. All of them are 0, which leaves bk. So let's go to a new slide here. B sub k. Okay, so that's what we have to calculate now. Okay, b sub k is equal to 2 divided by t, the fundamental period, times, again, we're going to split the integral from 0 to t over 2 because the definition of g of t changes at t over 2. So that's 1 times the sine of k omega t. And then we have plus the integral from t over 2 to t of g of t now is minus 1 in this interval times the sine of k omega t. I forgot my dt here, dt. Okay, so let's do this integration. So 2 over t times the integral of the sine is minus cosine with the inner part here. So minus 1 over k omega times the cosine of k omega t between 0 and t over 2. And then we have minus, right? That's from this definition of g of t. That's the minus sign here. So minus, now the integral here is negative 1 over k omega times the sine, times the cosine, right? The integral of the sine is minus the cosine. So cosine of k omega t between t over 2 and t. Okay then, so there's a minus here and a minus here. Let's combine them to a plus. Okay, so I'm going to just remove here this minus one. There we go. And then, well, let's plug in the bounds. So 2 divided by t times minus 1 over k omega times the cosine of k. For omega, I'm going to substitute in here already the 2 pi divided by t, right? That comes from up here. So 2 pi divided by t times the upper bound, that's t over 2. Okay, and then minus the cosine of k times 2 pi divided by t, that's the omega, times 0. Okay, that's the first integral. And then plus 1 over k omega times the cosine of k omega, but omega is 2 pi divided by uppercase t, the fundamental period, times the upper integration bound, that's uppercase t, and now minus the cosine of k times omega, omega is 2 pi divided by uppercase t, times the lower integration bound, that is t divided by 2. Okay, I'm going to close all of these parentheses. Okay, good then. Let's look at all of these individual terms. There's a 2 here divided by 2 and a t divided by t. So I can X those out here, right? They cancel against each other. Here I have a cosine of 0. Over here in this term we have t divided by t. So we can cancel this. And then in this last term, there's a t divided by t and a 2 divided by 2. So those can be cancelled here as well. And I am left with 2 divided by t times minus 1 over k omega times, okay, so let's see, the cosine of k times pi minus the, here we have the cosine of k2 pi over t times 0. So that's always the cosine of 0 plus 1 over k omega times the cosine of k times 2 pi minus the cosine of k times pi. Okay. So let's go through this one by one. So we have 2 divided by t times minus 1 over k omega times the cosine of k pi. Okay, so k, as a reminder, the wave number was a natural number. So that could be, let's go through this. So if k is equal to 1, so we have the cosine of 1 times pi, the cosine of pi. The cosine of pi is minus 1. I'll just keep track here over here. So if k is equal to 1, I have minus 1 for this term. If k is equal to 2, I have the cosine of 2 pi. That would be plus 1. So if k is equal to 2, I have plus 1. If k is equal to 3, then I have the cosine of 3 pi, that's again minus 1, and then k is equal to 4. Cosine of 4 pi is plus 1. So this term here, this term alternates between minus 1 and plus 1. And that depends on, right, if k, it's minus 1, if k is odd, and it is plus 1 if k is an even number. Okay? And then we have minus the cosine of 0, so that's minus 1. Okay? And then we have plus 1 over k omega times the cosine of k times 2 pi. So if k is 1, the cosine of 2 pi is plus 1. If k is 2, the cosine of 4 pi is 1, and so on. So this is always 1. And then we have minus this cosine of k pi, but we just found that that is equal to minus 1 if k is odd, or plus 1 if k is even. Okay, close this all out. So we'll get two different results. One of them if k is odd, and the other one if k is even. Okay, so let's see what we have. So that's equal to 2 divided by t. And let me factor out 1 over k omega, right? So in this first term here, I have a minus sign. Let me multiply this minus sign into this term here, into this parentheses. So I get 1, and then we have plus 1 if k is odd, and minus 1 if k is even. Right? That's because this minus sign gets multiplied on this term. That switches the sign up here to plus 1 minus 1, and it switches the sign here from minus 1 to plus 1, which I moved up here. And then we have plus the k omega was multiplied out, and we're just left with 1 minus minus, that's plus 1. So 1 plus 1 if k is odd, and minus plus 1, that's minus 1 if k is even. Okay, almost there. So that's equal to 2 divided by t. T was, let me just go up here again, 2 pi divided by t. Okay, so how am I going to do this? Well, let me just, let me leave the t here and instead substitute this for the omega like I did before. So 2 over t times 1 over k times omega, and omega was, there we go, 2 pi divided by t. 2 pi divided by t. So let's see what happens here. So this t cancels against that t, this 2 cancels against that 2. And then I have, let's combine all of these. So if k is odd, then I have 1 plus 1 plus 1 plus 1. So that would be 4. So 4 if k is odd. And let's see down here, if it's even, I have 1 minus 1, that's 0, plus 1 minus 1, that's 0 as well. So that would be 0 if k is even, this entire thing. Good, so that means now for my final result that b sub k is equal to, let's look up here, what do I have? I have 1 over k times pi, okay, so that would be times 4, so that would be equal to 4 divided by k times pi if k is odd, and 0 if k is even. Okay, so these are now formulas for any k value, right? So from k to 1, 2, 3, 4, all the way to infinity. If the k value is odd, then the b sub k, the amplitude of the sine, is 4 divided by k times pi, right? That k value that I'm looking at. But if k is even, 2, 4, 6, and so on, then the amplitude is just equal to 0. Okay, so let's look at what that actually does. How does that look? So here is the square wave. That's my g of t, right? In the horizontal axis, there's time, and in the vertical axis, there's the g of t. That is the function, the analytical function that I'm trying to transform. If I use just up to k equal to 1, my g of t is equal to my a naught, which is 0, plus all the ak's were 0 as well. And so if I don't go to infinity with my k, but just to 1, then I have this b sub k that I just calculated as it's an odd value. So 4 divided by 1 times pi. So 4 divided by pi times the sine of k omega t. K was 1. So I have an amplitude of 4 divided by pi that is well, a little bit over 1, right? That you can see here in the red curve. That amplitude goes above 1. And it's just a sine wave. Okay, and the example here is for a fundamental period t of 2. If I go up to k equal to 3, right? K equal to 2 won't change anything because b sub 2, right? K being 2, an even number, won't have any amplitude. So the next one would be at k equal to 3, which then for k equal to 3, I have an amplitude of 4 divided by 3 pi. But with a wave number of 3, so it has 3 waves per fundamental period. And if I add these two up, you'll see that I get a little bit better approximation to the square wave. Well, if I go to k equal to 5, the amplitude of the wave number 5 was then 4 divided by 5 times pi, so the amplitude gets smaller and smaller. But the sum gets closer and closer to that square wave. And here is the result if I go all the way to k equal to 7. But for the analytical case, right, I would have to add them all up until k equal to infinity. Thank you for watching.